Hello, everyone. My name is Calvin Carpenter, and today we're going to be doing the fourth homework assignment for computational methods. In part one or part A, we're going to be deriving Broyden's Jacobian update via the argument that updated Jacobian should have the same result as the original Jacobian on vectors perpendicular to the change in independent variables. So, hope you guys can see this screen, and I think my other camera's working. Okay, so say you have a graph. It's gonna be, how small is that? I'm still trying to figure this thing out. Okay, part A. Say you have a graph. Let it change to an eraser. I'm going to move that over. So you have a graph, and it relates a function to x. And say you have some random function on here, right? You've got 2 points on that. You have the previous point, and the new point. So this previous point is going to be labeled as x of k and f of k. And the new point can be labeled as x of k plus 1, f of k plus 1. Now, wow, that looks really bad. Hold on. It's hardly better, but you get the point. So as we've talked about a couple of times, a Jacobian is like in considering vector fields, it's the derivative in terms of the independent variables. And we can label that, or we can show that as j of k equals f of k plus 1. Oh, this is really close. Why am I doing this so close? Sorry. So actually going to flip this. Be better. So okay, jk, I'm still j of k equals f of k plus 1 minus f of k over x of k plus 1 minus x of k. So if we have the previous point in the function, then we can determine the new point in the function. And if we isolate for that, for f of k plus 1, then we'll get j of k times x of k plus 1 minus x of k plus f of k equals f of k plus 1. Now, in order to solve for this new point, x of k plus 1, right here, we need to set f of k plus 1 equal to 0. So we're going to have 0 equals jk times x of k plus 1 minus x of k plus fk. Scroll down so you guys can see. All right. But as we solve, you'll come to find out that this f of k plus 1 isn't actually exactly 0. But we make this assumption so that we can solve for that x of k plus 1, or the next value. And so in order to resolve for f of k plus 1, we can use the updated Jacobian. So we can rewrite that. F of k plus 1 equals j of k plus 1 times x of k plus 1 minus x of k plus f of k. So now we have the updated Jacobian involved. So now we're going to subtract these two equations and get a new function. So we're going to be left with f of k plus 1 equals j of k plus 1 minus j of k and then x of k plus 1 minus x of k. And just for future simplicity purposes, we're going to relabel this term as d. And that is going to be just equal to delta x. Okay. So now that we have this defined, we have to talk about something preliminary. So say you have just a point, right? We're gonna say that is x1, 3. If you were to travel upward to a point, let me move this down. I don't know why I keep doing that. That's better. Okay. So you travel up to a new point. We're going to call it x1, 4. You just traveled 1 unit upward. If you have an undefined shift of x that is perpendicular, I guess I shouldn't draw it like that. Your shift in x is perpendicular to your shift vertical. I lost my train of thought. Let me just draw it real quick. So we'll call this point, sorry, there's people outside. I was listening. Call this x2. X2, 3. And then this one's going to be x3, 3. So you have a shift in x, but you don't know which direction it's going to be in. But as long as the shift in x is perpendicular to the shift in y, the dot product between the two vectors is going to be 0. So that can be described as v times d, or it's not times, v dot product d is equal to 0. And you'll also be able to write v times v dot product d transpose is equal to 0, and v transpose dot product d is also equal to 0. So knowing this, we can obtain some additional information. Okay, so now that we have this information, I'm going to box that in because this is important. We can also say that JK dot V is equal to J of K plus 1 dot V. And we can rearrange that saying that JK dot V minus J. No, I'm going to do it the other way. Why did I erase that? Okay. What is going on with my iPad? Hello? Okay. Sorry. Technical difficulties. So we can write it as J of K plus 1 dot V minus J of K dot V is equal to 0. So J of K plus 1 minus J of K, and then this whole term times V is equal to 0. So if we look back up to, wait, I forget if I start recording. I did. You look back up here to this equation right here, this f of k plus 1, we're going to be able to use that. So just going to rewrite it down here. So f of k plus 1 is equal to J of k plus 1 minus J of k. And then remember, we substituted D in for that, in for delta x. So we're left with these two equations. All right, so now we're going to change around this equation a little bit. So move D to the other side. I'm just going to write it like this. So J of k plus 1 minus J of k equals f of k plus 1 over D. And then we're going to dot product the transpose of D. So using this, D dt is going to be equal to our absolute value of x squared, or sorry, delta x, not x. So yeah, that's right. Okay. Actually, I'm gonna rewrite this. I'm gonna say let's break it down further. So we're just gonna go D first, and that's gonna be equal to delta x squared. That's better. Okay. So now if we plug this back in, and isolate for our updated Jacobian to fulfill the information for part A, we are left with J of k plus 1 minus J of k is equal to f of k plus 1. So all we're doing is just substituting x back in for D. So f of k plus 1 delta x t over delta x squared. So now isolating for our desired term, the updated Jacobian, we're going to have J of k plus 1 is equal to that term, so fk plus 1 delta x transpose over delta x squared plus j of k. So this is going to be that's a terrible star. This is going to be our final desired result for part A. And we'll see you in a minute for part B. All right, so we're back for part B, where we are going to derive Broyden's Jacobian update as the minimum Frobenius norm update constrained by the secant condition. So, as previously derived, I think I remember what it was. We had f of k plus 1 is equal to j of k. This is for the updated Jacobian, by the way. J of k plus 1 times x of k plus 1 minus x of k plus f of k. So now if we rearrange this a bit and substitute our d back into this delta x, which we defined in the previous part, we will have delta f is going to be equal to j of k plus 1 d. This is going to be important. Also, we have this equation. J of k plus 1 is equal to j of k plus u v transpose. So we're going to use these two equations as previously derived in this part. Okay, so our current goal is going to be to minimize j of k plus 1 minus j of k. This is going to be our goal. And we can do that by taking the partial derivative and setting it equal to 0. So we're going to write this definition. So j of k plus 1 minus j of k squared is going to be equal to, that's a u, not a v. That looks like a v. Okay, so u vt squared. Okay, so I'm also going to throw this equation out there. So u vt is equal to this guy. This will be useful later on. I'm just going to throw it up here in the preliminaries. So now we're going to substitute this jk plus 1 value, the updated Jacobian, into this. And we're going to isolate for u and put it in terms of v so we can take the partial derivative. So delta f, wait, let me scroll back down. I'm recording, right? Yes. Okay. Dang it. Oh no, I hate when I do that. Just leave it up there. Delta f equals j of k plus u vt times, I'm pretty sure it's d. Yeah. Delta f equals. Yeah, okay. Sorry. Little brain fart. Anyway, we're going to substitute d in through the terms. How much time do I have left? Like a minute. Oops. Let's try and do this quick. Delta f equals jk d plus u v t d. And now isolating for u, delta f minus JKD divided by U, nope, divided by VTD is going to be equal to U. And for convenience sake, in the future, we're going to set this equal to H. So U is equal to H over VTD. Okay. So this can be kind of reorganized a little bit. So I'm going to rewrite it using what we wrote down right here. So it's going to look something like this. All right. Okay, so now we're going to take this equation and we're going to square it, and then, so like indicating what we did here, and then we're going to substitute U in for that. So if we square it, we're going to get U VT squared is going to be equal to we're going to be left with this. And then if we substitute our U value in for it, then we're going to have actually, I'm just going to do H squared. Okay, so we're going to be left with that. Now, if we distribute, then we will have our final terms. So we're going to have we're going to be left with this. And then, so this term, we're just going to make it equal to an arbitrary value or a const, or we're going to substitute in a letter to represent this value. We're going to use B, just because I want to use B. No particular reason, but it'll make it easier for the future. So now if we take the partial derivative, oh my goodness. I'm really bad at drawing these. In terms of Vm of B, and M is from anywhere from 1 to N. It could be any number of B, and we set that equal to 0. Then, since this, just because, oh, I'm sorry, I keep forgetting that I'm on the iPad. So we're trying to minimize JK plus 1 minus K, or JK plus 1 minus JK. Taking this derivative and setting it equal to 0 will help us minimize that, as we've said before. Okay, so now if we take the partial derivative, we're going to be left with take it in terms of VM. Forgive me if I make any errors. It's been a while since I've written out a partial derivative. Why do I keep doing that? And this is going to be multiplied by so that -2 is coming from like right here. And then I'm gonna have this. We're gonna be left with this as our partial derivative. Actually, this value is going to be squared. So now we're going to try and separate common terms. So in both, we have, actually, I'm going to do this in red so you can see it better. Or I could use, let's use highlighter. This term, we have these guys. We've got the 2. Then we've got this guy, and this guy is going to become a 1. So now if we take all that stuff out, we're going to be left with this. Yeah, that looks about right. Remember, this is equal to 0. Left 8. Jeez. Something looks wrong. Aha. Here, I'm gonna just take this whole thing and move it over. So we forgot our VM somehow. Anyway, so we're left with this. And since this term is being taken to 0, we are able to assume that this is going to be 0, so we can just get rid of it. Leaving the term VM minus a squared dm over leaving this guy. Okay. So now we're going to set all this stuff, all this good stuff, equal to alpha. So that leaves us with VM minus alpha dm equals 0. All right, so we're going to get VM equals alpha dm, which also transpose is going to equal to alpha times the transpose of d. That's going to be important. So now, if we take our original equation, the jk plus 1 equals jk plus uvt. So jk plus 1 equals jk plus uvt. We can substitute u and vt back into this in order to get what we want. So let's do it. So jk plus 1 equals jk plus, and then what was our u? It was h over vtd. That times vt, which is alpha dt. So substituting that h back in, we're going to get, yeah, I'm recording, right? I know I've checked this like 30 million times. Okay. jk plus 1 equals jk plus, and what was h again? It was delta f minus jkd. So delta f minus jkd over vtd. And then times, I'm just going to put this up top. So alpha dt. Wait, no, that's times this whole thing though. That would have been bad. Okay. So now we're going to substitute vt into here as well. So jk plus 1 equals jk plus delta f minus jkd times alpha dt over, and then our vt was alpha dt. So yeah, I'm forgetting a d. Okay. I was wondering why that looked weird. Anyway. So this alpha can be canceled. And then we're left with jk plus 1. And remember, d is equal to delta x. And this d dt, remember, that's equal to that, remember? So jk plus 1 equals jk plus delta f minus jkd times dt over, I'll substitute the other delta x's in there at some point. So delta x squared. And then finally, can do it all now. So delta f minus jk delta x over, I'm just going to put the delta x t over here, over and that should be the equation we are left with. So this is what my professor calls a yabba dabba do moment. So this is our final equation that we need for part B. Let me just give it a little give it a star. Part B. So I will see you in part C. Okay, so part C, it says to explain the geometric rationale for Lagrange multipliers and use it in conjunction with Broyden's method to find the minimum of the 2D Rosenbrock function, constrained to a circle center at 1, 1 with radius of 0.5. So, starting off, say we have a function f of x, and this is a function that we want to minimize. So, I'm recording, right? Yes. This is a function we want to minimize, but we can only minimize it using g of x, which is our constraint. So it can be defined that the gradient, not g, of this function is equal to, this is going to be Lagrange multiplier times, not that, times the gradient of our constraint. Okay, so when you look at, this is just from the Lagrange multipliers Wikipedia. If you look at this picture that they have, it shows our constraint function, g of x, and our function that we're trying to manipulate or minimize, f of x. And as you can see, at this point right here, this is the only point where the gradients are collinear between the function and the constraint. And so it can be defined that at this point is where we will find our minimum for f of x. Okay. So take a look right here. This is going to be our Lagrange equation. So we have L of x, y, and the multiplier are equal to f of x and y. I forget if these are gradients or not. They're not. Okay. So f of x and y plus the multiplier g of x and y. Okay, so now if we take the partial derivative of the Lagrange in terms of each variable, so x, y, and multiplier, say these are 0. All of this will mean that the gradient of f of x can equal negative of the multiplier times g of x. So I forgot to include y. Okay. That looks like it's a minus. I'm just going to take these zeros out. Use this with this guy. So now if we look at the Rosenbrock, This is just the Rosenbrock function Wikipedia page that I found. Basically, it helps us find minima. So in our problem statement, it was defined that the Rosenbrock function was constrained to a circle around center 1, 1 and radius 0.5. So that means if we take this function, and I can't really draw here, but at 1, 1, here, I'll just draw it on here. This is going to look bad, but you'll understand. You'll get the point. So if you have a graph, what does this kind of look like? Yeah, I'm just going to do like 0.5, 1. That's all we really need. Why did I do that? Okay. Just give me a second. I'm just drawing this real quick. Forgive me. Okay. Almost done. This is going to look terrible. I'm warning you. Carlos, don't make fun of me. Okay. Great. Sorry. So we have a center at 1, 1 right here. Basically, our problem statement is saying it's constrained to a circle center at 1, 1 with radius 0.5. So if we have a circle at this 1, 1 and we have a radius of 0.5, let's just make the circle a little bit bigger. Let's say that has a radius of 0.5. So that means that our local minima will travel somewhere down here. And right there, it means that our local minima will fall somewhere between 0.5 and 1. So hopefully this makes sense. Now we're gonna get to coding. I will see you over in collaboratory. So now that we've figured out that our function is going to be minimum is going to be somewhere between 0.5 and 1, let's do a little coding to prove that. So now we're going to import our necessary libraries. Import numpy as np. Import jex as actually don't need that. Okay. Actually, I think this is supposed to be import x GNP. Yeah. Import from button subplots. Import make subplots from optimize. Import minimize. Let's shift enter. Oh geez, I already screwed it up. Hold on, guys. So I needed this here. Okay, so now we can move on to the next part. Then we're going to define our Broyden function. Comma x1 max ter 100 comma DOL is equal to 1 minus 10. Make sure to include the colon this time. Pretty sure I screwed that up last time. So this is going to be the initial evaluation of the function and its norm. So FVAL, we're going to call it that final value 1 is equal to f of x1, which we defined in our function. Final value 1 norm equal to JNP dot Lagrange dot norm function of f val 1. So this is the one that's going to be evaluated. So next we're going to initialize the Jacobian approximation entity matrix JINV one dot size. Okay. Okay, so now we're going to do the main iteration loop for this function. For I in range okay, max iter teach step using the Jacobian approximation. The approximation x equal to negative JINV vector multiplied with FVA1 as defined before. So we're going to do a line search next that finds the step size that reduces the function value. So we're going to for loop inside of the for loop. So for j in range, and I'm going to repeat this 10 times. X2 is equal to x1 plus dx. F the AL2 is equal to f of x2. Norm is equal to JNP dot Lagrange dot norm about 2. So now we're going to check if the new function value is smaller than the previous value. Okay. So if the FL2 norm is less than FL1 underscore norm, we're going to break if this is the case. We want the for loop to continue. This is for reducing the step size necessary. So now it's now going back to the far left. We're going to print the, oh, this is supposed to be a comment. Information. About 2 underscore norm. If the function value is below the tolerance. E dot Lagrange dot norm. F val 2 is less than TOL. On so now we're going to reshape vectors future mutations. Okay, so these values, these lines actually need to be in here. That's why they're not defined. Okay, so now we can reshape the vectors for future computations. The x is equal to x reshape -1 to 1. F is equal to F1 reshape -1. Now we're going to update the Jacobian approximation using Jacobian not Jacobian, Broyden update formula. JINV is equal to JINV plus x minus JINV vector multiplied with df. And that whole thing is vector multiplied dot product with dx dot t JINV divided by dx dot t multiplied with JINV and then df. I actually forgot to make these t's capital. Next. Now we're going to update the current solution and function value. 1 is equal to x2 and f val 1 is equal to f val 2. Okay, let's try this out, see if this works. It works. So we're going to define the Rosenbrock function. V. Okay. We're going to unpack the variables x and y from v. X comma y equal to v. So compute the Rosenbrock values. Well, equal to 1 minus x. Yeah. So this should be our Rosenbrock function here. Make sure it works. Okay, we're good. So next, we're going to define the constraint function. And that from the previous, that is going to be our G right here. So DEF constraint V. We're going to unpack once again variables x and y from V. And so x, we're going to do the same thing as above, x comma y is equal to V. Now we're going to compute the constraint value. So results equal to x minus 1.0. minus 0.5. And results. So that's our constraint function defined. There it works. Okay, it's good. Okay, so now this is the initial guess for the optimization for our minimization. X guess is equal to JMP dot array 0.1, 0.1. Okay. We're going to minimize Rosenbrock function to the constraint. RES equals minimize. A Rosen function, X guess. Constraints is equal to constraint okay, so we successfully ran our initial guess optimization and our RES function. So now we are going to define the Lagrange. Define Lagrange. Okay. Next, the Lagrange from vector V. -1. Keep the Lagrange as a sum of the Rosenbrock function and the products of L and the constraint function. Rosen V 2 plus L times constraint V 2 term results. Okay, it worked. Lagrange underscore Jack equal to Jack's dot Jacobian Lagrange. Okay, that worked. So now Broyden Lagrange underscore JAC Yes. 1. Okay. So this should run. And we do have a matrix, an array. This does not look right. Okay, so here, I actually found this. I think this is what I want for. If this works in app. Ah, it's running like it should. And as you can see, our simulation here came down to an answer of 0.7527. And as we discussed before, we expected that the answer would be between 0.5 and 1 for the local minima. And so 0.75 makes sense. But this has been part C. Thank you guys for watching. I think that pretty much wraps everything up.